So in this video, we are going to understand a new type of algorithm design paradigm known as the dynamic programming algorithm design paradigm. So in this video, we are going to study dynamic programming. And to understand why such a new design paradigm of algorithm design, we're going to go with an example problem. We'll try to solve this example problem with our own existing algorithm paradigms, and we'll see that how existing algorithm design paradigms fail to produce a reasonable solution for such a problem. So existing paradigms fail. Then next, we're going to motivate dynamic programming, and in a way of solving this problem, we are going to go over some principles of dynamic programming, like how is a dynamic problem different from a greedy or, let's say, divide and conquer type of design paradigm. And then we'll solve the problem, solve everything regarding it, and then we'll come to the essence of dynamic programming. So that's the agenda for today. So here's some sample problem that I have for you. Suppose I have a path. Path is just a sort of a linear graph, and each vertex of this path has some weight. Let's say 1, 4, 5, 4. Now what my problem is to find maximum weight graph such that no adjacent vertices are picked, right? So okay, how would we go about doing such a thing? Let's say we go by a greedy design, that is, make myopic decisions and hope that they turn out to be true in the real sense, in the way that they turn out to give the correct solution. For example, when we studied minimum spanning trees, we used greedy decision procedure to pick whatever the next edge, whether it be prims or whether it be cruscals. We always took whatever the cheapest possible thing we had, and we hope that it results in a correct algorithm. So let's try that. So what our algorithm will do for this graph, it will first of all pick the 5th vertex, because that is the maximum weight that currently has. Now it would pick the 4th vertex, but because we cannot pick any adjacent vertices, it will skip both of these vertices, 4 and 4, and then it will go and pick this left one. So as you can see, by greedy we get the maximum weight as 6, but I don't think it's very difficult to show you that is not indeed the correct answer. The correct answer is actually pick 4 and 4. So for sure greedy did not work for this. Something else, maybe divide and conquer, in which what we do, we split it into 2 and solve both halves correctly, and then hope that they result, and when we reconcile them, hope that it gives the correct solution. For example, sorting and merge sort. We split an array into 2 halves, sort both of these arrays, and when we combine them both, it results in an n log n algorithm rather than a n square like any other sorting algorithm. So we split the graph into 2 halves, right? 1, 4, 5, 4, and smack in the middle. So on the left, the algorithm correctly gives me 4 as the output, and on the right, the algorithm correctly gives me 5 as the output. Maximum weight path for this and maximum weight path for this. But then when I try to combine them, they both are adjacent, and there is no immediate way to figure out how to reconcile them, or how to change my existing solution in order to accommodate for this clash. And as well, for this particular example, you can say that it's easier. I mean, go, instead of choosing 5, you can choose 4, but it's much difficult for a larger graph, because switching this may result in some changes in a much bigger 8 node graph, and switching that may result in a much bigger change in, let's say, a 32 node graph, and so forth. So in a bigger graph, this turns out to be a rather difficult thing to do, and we have no idea on how to optimally reconcile, or how to optimally choose the best output for the short answer that will also be correct for the bigger one when we start to combine them together. So clearly divide and conquer does not work, but brute force does work. What you can do is just search all possible independent set graphs, and then compute the maximum, and that by design will give you the correct answer. But then it's a very lengthy algorithm, and we are not interested in that. So definitely this motivates for something new. This motivates for something out of the box. So what do? Well, we run this thought process in our mind. For example, if we have an n node path, we have this thought experiment in our mind as to what the ideal solution will look like. Well, an ideal solution will look like, there are some choices of nodes. Some of them are excluded, some of them are not excluded. For example, maybe this one is there, this one is there, then 2 are skipped, then this one is there, and then this one is not there. Perhaps this is the correct answer, or something like that. So when we have nodes laid out to us in front in such a manner, we can always think in terms of, let's say, the last node. By design, because this is the last node, it can be quite easy to just look at this particular node, because there is nothing to the right, and this is basically the end. So in an ideal solution, I might have this node, or I might not have this node. Like in this particular solution, I did not have this node. It is possible that the correct answer was this one, and then the last node for a particular graph. And so the last node was present. So my point is, it is possible that in a graph G, if I have vertices labeled as v1, v2 up till vn, the ideal solution, the optimal solution, might have vn or might not have vn. So there are two cases. So let's look into each of them. If a graph does not have vn, so if this is my path, 1 2 3 4 5 6, this is vn, this is vn minus 1, and this is v1, let's say. If my graph does not have vn, then it's as good as solving a problem with only vn minus 1 nodes, right? Because it does not make a difference whether I include this in my original problem or whether I do not include this, because this was not in my optimal solution. So it does not matter as far as the algorithm or as far as the output is concerned. So let's say I have a g dash, which I define as g except the last vertex, and let's say my s dash is the optimal solution for g prime. My s dash is optimal solution for g prime. So I think it's a very cool, very, very, very straightforward next step, that if s prime is optimal for g prime, s prime is also optimal for g. Because the only difference between g prime and g was adding a vertex vn, which definitely does not make any change in s prime, because that was not included in the optimal solution. So if vn is absent, just solve for the first n minus 1 vertices, And that is the correct answer. Indeed, that is the correct answer. Okay, so that was case 1. Case 2, if Vn is present, well, in such a case, what happens is, this is Vn, this is Vn minus 1, this is Vn minus 2, and this is V1. If Vn is going to be present, then Vn minus 1 can definitely not be present, because then those are adjacent vertices, right? And let me define G double prime as G except Vn and Vn minus 1. So my next claim is going to be, if my claim next is going to be, let me just rewrite it, G double prime is G minus Vn and Vn minus 1. So my claim is, if S double prime is optimal for G double prime, then S double prime plus Vn is optimal for G. Because in the end, what I'm doing is, whatever is the optimal solution for this smaller problem, I'm just going to add Vn to it, because Vn was present in the optimal solution by our case analysis and Vn minus 1 was not present. So excluding these two vertices, if I have the smaller graph, I know the ideal solution to this, and I add up this particular Vn to that, and I have the ideal solution for the entire graph G. So solution for G in our thought experiment looks like this. If Vn is present in the solution, I mean, I'm referencing solution in the solution, but let's just, it's a thought experiment, so we can do whatever we want. If Vn is present in solution is equal to G minus Vn minus Vn minus 1 plus Vn. I mean, the solution for, suppose solution is a function which returns a solution for the graph. So if Vn is present in solution of G, then solution of G is equals to solution of G minus these two vertices plus Vn. Else solution of G is just solution of G minus the last vertex, right? So if you think about it, we are just basically just doing brute force search, but I'm just representing it in a very fancy if else fashion just to sound cool on YouTube. But if you think a little bit more deeply about this, there might be something to it actually. So let's see why. For example, for now we do not know, right, that if Vn is present in the solution or it is not present in solution. For now we have no clue on that, and we are just going to rely on a genie in the magic lamp to tell me what is going on over here. But nevertheless, I hope that it is very clear that what I'm doing in these if else loop is just doing a brute force search, but in a very differently expressed manner. And to make that very clear, I'll also draw a graph for you to see. But while I draw this graph, while I draw this tree, it will also be very clear to you what dynamic programming achieves. So for example, I'm solving right now for n vertices, right? And there are two possible solutions. Either I'm going to solve for n minus 1, or I'm going to solve for n minus 2 and then add that. So that's a post-processing step, adding that last vertex too. Now when I'm in this particular sub-problem, so when I'm not looking at any other thing, if I were to only send solution of G minus n minus G minus the last vertex to my solution function, it will again make two branches. Either it will solve for the first n minus 2, or it will solve for the next, n minus 3 problems, right? When I'm in this n minus 2 solving paradigm, it will either solve for just the last vertex removed, that is n minus 3, or it will solve for the last two vertex removed, that is n minus 4. And when I solve for, let's say, n minus 2, when I'm in this particular vertex, only this, the one where marker is, either I will solve for n minus 3 or I'll solve for the n minus 4. And similarly hit n minus 4 or n minus 5. And similarly here n minus 5 or n minus 6 and n minus 4 or n minus 5. So as you can see, there are a lot of redundancies here. For example, n minus 2 has been solved here, but is also being tried here. Similarly, n minus 3 has been going on here, here, here. N minus 4 goes on here, 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 and here. N minus 5 is here, 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 and so forth down the tree. This will start to, proliferate. So do you get the idea? It seems that we are doing a lot of redundant work, and if maybe in some way we can harness the work which was already done before. For example, when we were, let's say, very deep in such a branch where we were solving for n minus 10, and from that we can come up and we were building n minus 5, and somehow we stored the result that was for n minus 5. We can use it here and here and here, and similarly for n minus 4, and we can store the result for n minus 3 and use it here, 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 and so forth and so forth. Right? You can see what is being tried over here. So the point is that we are actually only solving for n distinct problems. Because there are only n distinct points, we are never solving for more than n distinct problems. And I am saying distinct because here, as you can see, it's going to grow to a very deep tree of 2 raised to the nth power. But then in the end, the only distinct problems you are solving is n. For n or n minus 1 or n minus 2 or n minus 3 or n minus n. Only these n problems are being solved for n minus 1, sorry. So n minus 0, so this looks like a clean way of showing that. So if we can somehow store previous problems, we can access them in constant time and use that to speed up our process. And this technique is known as memoization. Well, not memorization. It should have been memorization, but it's just called memoization. So instead of, you got the feel, you understand the feel that what we're trying to do. We're going to solve this bigger problem in terms of smaller problems, and whenever we solve a small problem, we're going to cache its results, and whenever the result is needed, we're just going to access it in constant time. But a better way to do it will be do it in a bottom-up fashion. For example, if I have this path, what I'm trying to say is, if I have this path, solve for the first vertex, then solve for the first two vertex, then solve for the first 3 vertex, then solve for the first 4 vertex, then solve for the first 5 vertex, and so forth, in a bottom-up fashion. So what we're going to do, in a very pseudocode way, I'm going to assume, let's say I'm going to, this is a nomenclature. Gi is the graph consists of first I elements, right? So what I'm going to do is solve for G1, then solve for G2, then solve for G3, then solve for G4. So let's say I have an array A of n elements, and it's initially an empty array. A of 0 is 0 because having 0 elements is just going to be 0. A of 1 is V1 because this was just the first element, right? Now comes the good part. A of 2 will be what? A of 2 will be whatever is the better solution of these two. That is, in those two cases, whatever is the better solution. So the cases were, let me just find them. I did write it in an if-else fashion somewhere. Yeah. So if the last vertex is present, then remove the preceding two vertices, and whatever is the best solution for here, take that. If it is not present, then include the best solution for the just excluding the current vertex. So what it will be whatever is the better of in these two options, v2 plus a of 0 or a of 1. Do you see what I'm doing here? I've excluded the last two vertices when I'm in this case, and I've excluded the current vertex, that is just the v2 vertex, when I'm in this case. And similarly, A3 will be whatever is the better of these two, v3 plus the array of 1 or the array of 2. So if I'm going to write it in a for loop fashion, a of 0 was 0, a of 1 was v1, and for I going from 2, 3 up to n, a of I will be maximum of a of I minus 1 or a of I minus 2 plus, say with me, v of I. Now let me trace back, let me loop back and let me show you why this is correct. Let me try to get that intuition for you. I'm going to lay it out in a very step-by-step manner. So the aim was, what we wanted to do was analyze in a case-by-case fashion. Either the last vertex is present or the last vertex is absent. If the last vertex is absent, then whatever is the solution for my graph is still the same solution if the last vertex was absent. So basically I minus 1 in this case. If the last vertex was present, then remove these two, and whatever is the best solution, have that. So I minus 2 in our array notation, right? And I am going to say that is going to be the ideal solution for a particular graph, because we are doing the case-by-case analysis. So if Vn is present or it's not present, and how do we decide to include Vn or to not include Vn? Well, by the max operation that we are going to do here, that we are doing over here. So the idea was, the meat of the entire dynamic programming thing is that instead of solving a entire brute force method, we're just going to solve the n problems, and then we're going to cache their results and use them as and when needed. So for I equals to 0, the ideal solution is 0. For I equals to 1, the ideal solution is, well, the vertex itself. But for I equal to 2, the ideal solution will be either this or that, and for I equals to 3, it will be this or that. So let's try, instead of keeping that on pseudocode, let's try to be the computer and do it on our answer, do it on our demo problem. So it was 1, 4, 5, 4, and I'm going to populate my array here. So a of 0 was 0, a of 1 will be 1, a of 2 will be maximum of excuse me, 6th page go, okay, something is missing. Oh, it's here. Okay, so a of 2 will be, I was looking for this. A of 2 will be whatever is the maximum of v2 plus a0 or a1. So what is v2 plus a0? v2 plus a of 0 is 4, and a of 1 is 1. So this is going to be 4. What is going to be a3? a3 is going to be maximum of v3 plus a1 or a2. v3 plus a1, that is 6, or a2. that is 4. So here the input will be 6. What is this going to be? The last one, it will be maximum of v4 plus a of minus 2, that is 4, 8, or this previous one, 6. So the answer will be 8. And now we just pluck this number off at the end of the array, and we know that a8, I mean the last element of the array, will give me the ideal number for maximum weight graph. So the answer is 8. So as a sanity check, we know for sure that the algorithm is resulting at least the correct answer for our demo problem. And the main argument, for me, I think the main switch of the algorithm was going from step 3 to step 4. So as far as step 3 is concerned, I think we are all understanding that for 0 it's 0, for 1 is 1, for 2 is 4, for the third one it's 1 and 5. This is also what the greedy algorithm would have outputted for the three vertices. But here is where dynamic programming comes in clutch. For example, I mean, it has simultaneously analyzed two possibilities: either exclude the last vertex and simply carry on with the result present here, or include the last vertex, go 2 steps back, and then pick the best solution there. So that was 8. Let's try on some other, let's say a bigger problem. 6 vertices, let's say 1, 2, 3, 5, 8. I'm writing it as a Fibonacci numbers, but I'll not use Fibonacci for the last one. Let me make this 7. Yeah, seems good. So what will be the maximum weight graph for this? Let's go the dynamic programming way. Let's not try to do it our own way, because I might end up trying to solve it by a greedy paradigm, and that's not what I want to do. For 0 it's going to be 0, for this is going to be 2, for this is going to be 2, for this it will be either 2 or 3 plus 1, that will be 4. For this it will be either 4 or 5 plus 2, so it will be 7. For this it will be either 7 or 8 plus 4, right? Because either it's this or it's this minus 2. Either it's carry on from the previous element, or it's this minus the last 2. Either it carries on from the previous element, that is 2, or it is 3 plus 1, 4. Either it carries on 4, or it is 5 plus 2, 7. Either it carries on 7, or it is 8 plus 4, 12. Either it carries on 12, or it is 7 plus 7, 14. So it looks like this is the one. 7 plus 5 plus 2, that is the correct one. If I were to do some value changes, perhaps it would have been different. For example, if I were to choose the last element to be 4. Oh, this seems interesting. 1, 2, 3, 5, 8, 4. Let's try this. 1, 2, 3, 5, 8, 4. 1, 2, 3, 5, 8, 4. For this it will be 0, for this it will be 1, for this it will be 2, for this it will be 3 plus 1, 4, for this it will be 5 plus 2, 7, for this it will be 7 or 8 plus 4, 12, for this it will be either 12 or 4 plus 7, 11, so it will take 12. So in this case the answer is this one, right? And our dynamic programming algorithm results in a very correct way. But still there might be a question in your mind that we have not resulted in actually the correct answer, the correct set, the correct number of the correct vertices. All you are outputting in the end is the maximum weight graph. Oh sorry, maximum weight for that graph. So how do we go about constructing this? So one idea is just backtrack the entire process. So just go in a backward fashion and backtrack it. So if the value for the current cell in an array is same as the previous one, skip that vertex. If the value has been increased from the previous to this, that means there was some sort of a skip connection. That means there was some skipping that was involved in the process somewhere. Because if you see in this example, there was always a decrease in number. That means there was always skipping of some sort. In this example, there was always skipping up till the last point, in which we decided not to include the fourth but include these solutions. So if there is a constant sort of from going from one step to other, that means this one has been excluded, so take this one, and then go on so forth. So a backtracking algorithm is clearly very easy to make, and let's make him. So let A be my filled array, right? So while I is greater than 1, because I'm going to go from front to back, I'm going the back way, so this is going to be my thing. So if A of I minus 1 is greater than equal to A of I minus 2 plus V of I, decrease I by 1, else add Vi to our solution set and decrease I by 2, I equals to I minus 1. So I hope you can see. So if I minus 2 is greater than, if I, for example, if I'm in this, if I minus 1 is greater than equal to I minus 2 plus Vi, then decrease I by 1. So it's the same thing. I mean, all I'm doing is comparing this and so forth. So this could have very easily been written in some other way also, but this works. I want you to spend a minute or two on this if you'd like. And so dynamic programming we understood. Example problem, existing paradigms we saw how greedy fail and divide and conquer fail. We motivated dynamic programming. I still have to give a comment on principles of dynamic programming. So essentially what we are trying to do is, in a thought experiment where we have genies to tell me what the real solution will look like, in thought experiments, think in terms of smaller problems. Think in smaller problems of the same problem, of the same structure. Solve those problems, solve smaller problems, store those solutions, and access when needed. Access, and also the access when needed is also true, but before that, the big problem can be solved in terms of the smaller problems. I'm sorry about my handwriting, but yeah, you can also hear me. The bigger problems can be solved in terms of the smaller problem. And now when we are solving those bigger problems, access when needed. Access the solutions to the smaller problems when needed, right? So here comes the essence of dynamic programming. This is what dynamic programming is all about. I'm just going to paraphrase this. I'm just going to read from my notes, which I've made while I was studying in the class. I mean, studying from the lectures. So the key ingredients are: identify a small number of subproblems, can quickly compute larger subproblems given solutions to smaller subproblem. So have a notion of what is smaller or what is larger. I've said the same thing here. And after solving all subproblems, can quickly compute final solution. So I'm not going to rewrite this again. Think in smaller problems. Identify first of all what is the structure of our problems and can it be broken down into smaller, and have that notion of this being smaller than this. So if it can be broken into smaller problems, identify those smaller problems. We can quickly compute larger problems in terms of smaller problems. For example, in this case, all there was needed to compute the larger problem in terms of small problem was this max function, right? Maximum. So that's a quick computation. So we can quickly compute larger problems given the answers to the smaller problems. and then after solving all the sub problems can quickly compute a final solution. That is backtracking in some sense. So this is what dynamic programming is all about, and I hope this video has been helpful to you in getting a sense of what we are trying to achieve with the dynamic programming design paradigm. Now in the next couple videos, in the next video we will also go through some other examples of dynamic programming. That is the knapsack problem. Like if you can see, the knapsack problem is just lined up next on this notes, and the sequence alignment problem, that is a DNA sequencing problem, and we'll discuss on that. Also optimal binary search trees, that is also a very nice application of the dynamic programming paradigm.